everybody. Today we're going to be talking a little bit about electron energy and the flame tests that we're going to be doing in lab together, our flame test lab. So a few of the things that we're going to be looking at with electron energy, it's going to start with the visible light portion of our electromagnetic spectrum. And I have it taped up here for you. I'm going to bring it a little bit closer. We're going to be using this in our flame test lab, but I want you to remember that on the lower energy side here, in the longer wavelength, we have infrared radiation, which leads into the red portion of the visible light spectrum, all the way to violet. And right after violet, the portion of the electromagnetic spectrum, visible light portion, we have ultraviolet. Now I want to point this out because I want you to be able to see that we can actually measure the wavelengths of all of these portions of that EMS, the spectrum. You see that over here, if you have a wave that's about 800 nanometers, it would be in the infrared portion. 300 would be ultraviolet, and in between we have that visible light. Okay, so we can actually use a graph like this to estimate, if we see certain colors, about what wavelength that light is traveling at. So we're going to see that again in a second. But I did put a general outline of the wavelengths for each of the ends of our spectrum. So the red end is about 780 to 622 nanometers. The violet end being 455 to 390 nanometers. So we see that this is a longer wavelength for the red side and a shorter wavelength, 390 nanometers, for the violet end. So we're going to be looking again at, we've seen some information about waves. We're going to be looking one more time at waves a little bit. So when we're talking about light and we're talking about energy, we see that all portions of the electromagnetic spectrum, they have this wave-particle duality. And we've talked about it briefly, but it basically means that they all behave like waves and they all behave like particles. Okay, so they have this duality about them. Neither is a good enough way to describe the way that they travel and the way that they behave. So both of them are used to describe the way that they are traveling, the way that they're behaving. So we see that all EMS travels as waves that have a wavelength, frequency, and energy. If you remember our wave diagrams that we saw last unit, we know that the peaks, or the very bottom peaks, are called our crests at the top and the troughs at the bottom. Between each of those peaks, either between the crests or between the troughs, you have the wavelength, and that's the actual wavelength that we're getting here in these measurements, is the distance between the waves. The longer the wave, we see the lower the energy and the lower the frequency. The amplitude, we don't actually talk about this much, especially with EMS, but it is just the height from a crest to that baseline, or from a trough up to that baseline, or to the middle of the wave. So when we look at wavelength, this is what we're primarily looking at this unit. We see that the red end of the visible light portion of the electromagnetic spectrum is long wavelength, where the violet is short. So long from about 780 nanometers to a short end of about 390 nanometers. The frequency, because the wavelength of red light is so long, the frequency is low, and therefore the energy of those electrons, those waves, are low. At the violet end, because we have a short wavelength, the waves are occurring a lot more quickly. We have high frequency and high energy, so they go hand in hand. Now, along with behaving like waves, we see that all EMS travels as photons as well. So they travel as particles of energy, in addition to just traveling as waves. Okay, so we're going to take a look at a little bit about what this means for the energy of electrons, especially in our flame test lab. So we heard in our POGO a little bit about this, but in case you don't remember, some lab terms that we're going to be coming across. The ground state of electrons. Now these are the electron configurations that we've been writing up until now. 1s2, 2s2, 2p6, all of that. We've been looking at the ground state configurations, specifically ground state, which are written according to Aufbau's principle, right? So the principle that lower energy levels fill first. So before you can fill P energy level, or P sublevels on an energy level, you have to fill the S on that same energy level. Before you can fill energy level 2, energy level 1 has to be full. So we write according to Aufbau principle, which means that the electrons that are closest to the nucleus, the ones at the center of the, or closer to the center of the atom, have the lowest energy. Those that are filling on the outer part of the atom, therefore, have the highest energy because they're being added last, right? Those are the energy levels that are being filled last. So those electrons in those outer energy levels have higher energy than the inner ones. Remember that the ones on the outer part of the atom we call the valence electrons, okay? So those are the ones we really care about because of bonding. Now, opposed to the ground state, there can also be an excited state electron configuration. And this is where electrons actually gain energy and they move up to a higher energy level before they should, right? Before that ground state would say that they should. It does happen, and we're going to see this in the flame test lab. Because what happens when those electrons gain energy and they jump to a higher energy level out of the ground state configuration, they eventually have to fall back down. Now, when they fall back down to that ground state energy level, they're going to release energy. We see that energy that they release as visible light, and we're going to see that as different colors of the visible light spectrum. So we'll be using this spectrum to identify what color we are seeing, and therefore the wavelength of the energy that's being released. So what is the energy being released based on that wavelength? So when those electrons fall back down to their ground state, they release energy. Now, we can look at, and we will in the lab, look at the Lewis structures and orbital notation for the atom and the cation that we're testing in the flame test lab, because we're specifically using metal cations to test in the flame test lab. Now, we've talked a little bit about ions. Specifically, cations are metal ions, okay? So remember that ions have different number of electrons, which make them either positively or negatively charged. A metal cation will lose all of its valence electrons. And the reason it does this is to achieve a noble gas configuration, okay? So it's going to lose electrons to be like these noble gases, right? So depending on where it is on the periodic table determines how many valence electrons it will actually lose. Magnesium, which we're going to look at in a second, is in the second column in the alkaline earth metals, which means it has 2 valence electrons. It's going to lose both of those valence electrons to gain the noble gas configuration. So when we look at magnesium, it has 2 valence electrons. When it loses those, its Lewis structure now no longer has those 2 valence electrons showing, but rather a 2+ charge, because an atom that loses 2 negative charges is now a 2 positive charge, okay? Because there's 2 more protons than there are electrons. Now, we've looked at the orbital notation for these, but we can take a look again and see magnesium again, right here. I'm going to scoot this over a little. Magnesium is right here on the periodic table, atomic number 12, so we need to show 12 electrons in our orbital notation. We see that the filling order will be 1s2, 2s2, 2p6, so up, 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 down, 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 and then 3s2 will take us to magnesium, so 1 up and 1 down. That is the ground state configuration for magnesium atom. We can also draw the ground state configuration for the magnesium cation. Remember, it's lost its 2 valence electrons. If we're looking at the 2 valence electrons here, it's these 2 electrons in that highest energy level in 3s. So the same configuration we'll have for Mg2+, except no electrons in 3s. So we'll have 1s2, 2s2, 2p6, up, 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 down, down, down. But this is magnesium 2+, which has lost its 2 outer electrons, these 3s electrons. So we have nothing in 3s. So we wouldn't actually even write 3s for this configuration because there are no electrons in 3s. Now, we're going to see a few exceptions to our electron configurations. And the reason I want to look at these is because we're going to talk about why there are exceptions in terms of electron stability, and because you're going to see one of these that we're going to test as a metal cation in the lab. So here, I've just, for the ease of showing you, I wrote out the predicted, what we would predict is the ground state electron configuration for a couple of different atoms. So we have chromium, we would predict, now chromium on the periodic table is atomic number 24 right here. It's actually the fourth element into the 3D block. So you see that the abbreviated configuration I put here is argon, followed by 4s2 and 3d4. It's the fourth atom into the 3D block. This is what we would predict with the configuration of argon, 4s2, 3d4. What we see actually happens is that we're going to, for chromium, specifically here for chromium, one of these electrons from 4s is actually going to pop into 3d. Okay, so it's not what we would predict, but we see that it's what happens. So one of the outer valence electrons is actually going to pop down into that 3d orbital, or sublevel. So we have, instead of 4s2, 4s1, and instead of 3d4, we actually have 3d5. 1, 2, 3, 4, 5. Now you might notice what this has done is it's taken a not filled 3d, and now there's a 3d fully filled, or half filled. Keep that in mind. The next one that we're going to look at is copper. Now, copper is the 9th element in 3D. Okay, so 9th element in 3D. So we actually see, again, argon, again, 4s2, and 3D, 9. 2, 4, 6, 8, 9. 3D, 9. So 4s2, 3D, 9. This is what we predict. It's not how copper actually is that we find. And this is one of our exceptions that we have come to discover, is that copper's configuration is actually going to be losing one electron from 4s, and it's going to pop over again to 3d. So now, instead of 4s2, we have, again, 4s1, just like up here with chromium. And instead of 3d9, there's actually going to be 10 electrons. So up, 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 and down, 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 down. Now what you see here is that instead of 9 electrons in 3D, now we have a fully filled 3D sublevel. Again, important. Other exceptions that we see, and I'm going to move this over so we can see where they are. Besides chromium, another exception is the element right below chromium, molybdenum. And we see that both of those are going to, unexpectedly, not what we expect, they end in D5, not D4. Now copper, right below copper, is silver and gold. All three of those in that same group that we would predict end in D9 actually end in D10. And the last ones are lanthanum and actinium, which, unlike we predict, actually end in, we would predict that they end in F1, actually end in, or start at, F1, they actually end in D1. Okay, so I want to look briefly at why that is, and it's all in terms of electron stability and what electron configurations are actually stable or unreactive. Because remember, all atoms, generally, they want to be like noble gases. Noble gases are unreactive. That unreactivity is what is stable. So, what are the most stable configurations? Well, like I just said, a fully filled p level. If you have a fully filled p level, you have the configuration of a noble gas. Okay, so fully filled p level would be P6, ending in P6, i.e. noble gases. Those are the most stable. What we see as next stable is a completely filled D level, okay, which would be ending in D10. Well, we see that's what happens up here with copper, is that instead of the predicted D9 ending, it actually has a D10 ending. This was 5, right? So it actually has a D10 ending. That is copper, silver, and gold. That's the second most stable configuration. And the third, a little less stable than these two, would be a half-filled sublevel, so D5. So really any half-filled sublevel, but D5 would give us chromium and molybdenum, just like we saw up here. Instead of the predicted ending of D4, chromium actually ends in D5, and that's because the atom is more stable in that way. The least stable configurations are anything unfilled, any unfilled energy levels, which is all else. So alkali metals ending in S1, alkaline earth ending in S2, and halogens, which are S2, P5, would be least reactive, or least stable configurations.